Okay. Hello. Thank you for coming. I understand that it's the last presentation today, and it's quite a specific topic. I'm going to speak about a relatively new feature in OpenSSL named UPSK. It's a feature allowing using opaque object as keys for symmetric algorithms. First, brief reminder, who am I? My name is Dmitry Belyavskiy. I work in Red Hat. I maintain OpenSSL and OpenSSH there. And my current tasks are mostly related with PQ transition. I have multi-year OpenSSL experience. I was a member of OpenSSL technical committee since 2021 until it was disbanded, and now I participate in OpenSSL advisory committees. You have heard the presentation from OpenSSL team just before my presentation, so you have overall understanding about OpenSSL governance. Now I want to make a brief reminder about OpenSSL library architecture. OpenSSL as a library provides two libraries, libcrypto, which has a wide API for working with ISN1, working with X509 certificates, and what is the most important for our presentation, so-called UVP API, which allows working with different algorithms. libSSL is a separate thing. We will not touch it in this presentation. It's designed for network protocols such as SSL, TLS, QUIC, you name it. But when we're speaking about OpenSSL, you see that libcrypto provides the end-user API, but all the algorithms are implemented in various so-called providers. It's a plugin. Basically, you can consider it as plugins. OpenSSL currently has three built-in providers providing algorithms. It's default provider. FIPS provider designed for FIPS certified systems, legacy provider which includes old algorithms that are either insecure or less popular, mostly insecure. But of course, the developers can implement their third-party providers. So we in Red Hat have implemented PKSS11 provider, which allows us using algorithm relied on hardware tokens, HSM, and so on and so forth. A brief reminder about two categories of cryptography. We have asymmetric crypto, which is used for various operations such as digital signature, key exchange, key encapsulation. You see the list of algorithms that are used for these purposes. The key feature of asymmetric algorithms is that you don't have one key, but you have a key pair, a private key which should not be available to anyone but its owner, and the public key which is public, anybody can access it, and you can make some operation using the private key and provide an opposite operation using public one. OpenSSL works with asymmetric algorithms well, forever, and the key structures for asymmetric algorithms are normally quite complicated, and it means that when the transition to the provider model happened, the opaque pointers became the most standard way to deal with it. You have a UPK object, and you have a set of callback structures in the providers that operate the particular operation with what basically looks like an opaque pointer to a library. Symmetric crypto implies that you have only one key for the operation. It's normally named the secret key, comparing to private. So we have the examples of such algorithms as symmetric ciphers, MAX, etc. So again, you have a list of algorithms on the screen. IS is the most important cipher algorithms. HMAC and CMAC imply that you use some low-level cryptographic algorithms such as hash for HMAC or symmetric cipher for CMAC, and a secret key as an input. And normally in OpenSSL library, keys were represented as raw bytes array. But, well, it's not always suitable to use a raw bytes array. When you have a PKCS11 token, and you often have it nowadays, you normally don't have an access to raw bytes array implementation, but you have something normally named handle, and you still want to make some encryption. Also, an example of this approach is HSM, hardware secure modulus, processor enclaves, TPMs, and so on and so forth. We have implemented PKCS11 provider, as I mentioned before, and working on it, we found out that no raw bytes array are not suitable and are not enough for our purposes, so we started working on it. One more example, even if you operate in pure software, you can try to somehow protect the keys from being found in memory in a raw way. You can use scheme masking or some other techniques. So that's enough to provide some rationale to support these keys. Of course, we could, using some hacks, implemented even in ancient times, pre-3.5 times. Well, I can write the code using all the OpenSSL API that would use handles for PKCS11 backed keys. Please don't do it. Don't try it. And since OpenSSL 3.5, we started adding the algorithms, so the possibility to deal with opaque objects. First, we added support for symmetric algorithms, but when you feed, before you feed the key as an input to the symmetric algorithm, you should somehow get it. Normally, you get the key using some asymmetric operation. It may be an output of some k derivation function. It may be an output from Diffie-Hellman-like scheme, which means that you have to you take your private key and Peirce public key and derive a key that then turns to be a part, an input of the symmetric key algorithms. The structure of the new added object is quite simple. There are two common attributes for ref counting, so we can use it simultaneously from similar threads, avoiding double freeze and so on and so forth. But then you see just two important structure members. Key data, which is opaque pointer, and UPSK management. It's a new structure. It's implemented in one of the providers. And this is the structure which knows how to void what is the real structure beyond that opaque pointer and can deal with it correctly. Its responsibility, for example, is import-export keys, operations, management, so on and so forth. New API. If you don't implement the provider, it's what you should basically read about. Man UP key. You will see that we have functions to generate opaque object. We can, of course, we should be able to import raw bytes when we have a key represented in raw bytes form. There are several functions which basically do the same, but taking different arguments depending on what objects we have in disposal. We can say that, well, we need to convert the keys that is implemented, is backed by one provider to a different one provider. We can try to get raw bytes from the existing key. This operation, of course, may fail, but you still may try. SK management structure, which is backend, which again you will not have to deal with it until you implement a provider. So again, it has a lot of standard structures, standard members of structure. Every provider structure has something like that: name, type, description, pointer to provider, ref count, destructor, yeah? And here are several specific routines that provide you the information which provider set, which parameter set you need to create a key, either from scratch or from some data. Export and import callbacks. Of course, you may want to generate the key from out of nowhere. And you normally, in some circumstances, need a string identifier of the key for printing purposes, for example. So, and you see these callbacks naturally match these requirements. Again, I will not speak a lot on the API part of the SK management. It exposes the function listed on the previous slide to the libcrypt API. You normally don't have to deal with it until you write code. You will have to deal only with OpenSSL API. But in case you really have to write code, you will get the problems. Yeah, you will have to support multiple algorithms in your providers, and in some cases you have to distinguish for what purpose do you generate the symmetric key. For example, yeah, IS has 3 allowed lengths of keys. 16, 24, and 32 bytes, and if so you can't generate 12 bytes key and use it for AS. So you have to make checks on the provider side. What's also a must in case you implement the opaque objects and support it in the provider is that you should support the import of raw bytes. And for export, you can't always export the raw bytes representation. Yeah, otherwise, well, if you always could export the raw bytes, you did not need this API. But you can use the export function to get some identifier, which then would allow you to recover the handle and use it for subsequent operations. OK, let's jump to particular API changes. These 2 functions were added in OpenSSL 3.5. When you use symmetric algorithms, you always have init functions that accepts keys. And so you see the natural change of the API, not change, basically an addition to API. Now you can accept the OpenSSL object instead of raw bytes array. Same for UEP-MAC. You had function UEP-MAC init. Now you have a function UEP-MAC init SKey that should take the SKey object. Again, briefly reminder that on the provider side we have callback structures. So it means that we need 2 more callbacks for the EOP cipher structure implementing symmetric ciphers and 2 EOP MAC which implement the MACs. What was added recently in the OpenSSL version 3.6 that was released, as colleagues says in the previous presentation, just in the beginning of October, about a month ago, is using the, not using derivation of the symmetric keys from the asymmetric algorithms. So as I mentioned, when we use some Diffie-Hellman-like scheme, we have our private key and Peirce public key, and if we have a hardware token, we may want to derive the key that will not leave the token, but still suitable for using in ciphers. For this purpose, we have the UPK exchange API, and again, we had function UPPK derive, returning row bytes pointer. Now we have added the new one that returns UPSK object. For KDF, let me remind you, provide some parameters. Some of them can be public, some of them are not public, such as passwords, for example. You have to implement 2 functions. Yeah, you may have that non-public parameters also represented in a format of UPSK. So you can set the, you can init the KDF operation using the symmetric key object. So the function UPKDF CTX set as key. And of course, after the derivation, you also may want to have an object that would persist in the hardware token or HSM and will not be available for direct access in a row byte format. And of course, again, yeah, you see we return the callback structures. We add naturally 2 functions to the UPKDF and 1 to UPK exchange. Fallback mechanisms. Yeah, it's also important. Yeah, OpenSSL declares that you can build provider for OpenSSL 3.0, use it with OpenSSL 3.5, and it will work. Well, to some extent. Of course, you can build it the way it would not work. Normally, you should not. Yeah, but it means that we should care what happens if you use the new API and you don't have the corresponding implementation on the provider side. Well, you don't have much choice. You have to try to export keys as raw bytes or get the pointer. And if it fails, well, you are unlucky. For new implementations, we strongly recommend support of both sets of callbacks for the opaque objects and for the raw bytes array. And well, if you have a key created in one provider and you have to use it with implementation taken from another, you have no other way than provide so-called export-import dance when you first get a pointer from one, well, raw bytes from the key, and then try to reconstruct an object for a compatible way to new providers. It's all done on the API label. It's all done inside the UP API. You don't have to perform this dance manually. Next steps. OpenSSL has an abstraction layer named store, which allows you to convert various representations. It may be a file, it may be a URI, it may be basically anything, into a key object. Well, when I say key this time, I mean both symmetric and asymmetric keys. After that, you use this object in a normal way with all the UP API. I have implemented a pull request. It's waiting for review. I hope it will be reviewed relatively soon. The problem is that there is no format specification for symmetric keys. Yeah? There are two basically dead specification. One is not implemented anywhere. The other has a quite limited implementation. Also, yeah, you have, well, when you set a symmetric key, if we don't take into account the length limitation, every sequence of byte can be a symmetric key. So yeah, you can have a file that is normally parsed as X59 certificate and feed it as a symmetric key calculating MAC. Don't do that. So it means that when we implementing this support in file API, this PR, which is still waiting for review, I can presume that we have some natural arbitrary value of max k length, and you have to explicitly request that, well, I read these bytes from file and I'm going to use it as symmetric keys. Otherwise, the format of detection, which is already implemented in OpenSSL, will work. Speaking of PKCS11 provider, you can use the standard PKCS11 URI format, and it just works out of box after some patches that have already been landed into PKCS11 provider. Okay, you never like to write C code, even if you have 11 at your disposal, right? Nobody likes writing C code. For some experiments, you are able to use OpenSSL command line utils. OpenSSL list is a utility that provides you the list of all types of algorithms available in this installation. I mean OpenSSL library plus third-party providers, plus native providers, of course. We have implemented OpenSSL skutil to work with symmetric keys, but it's of quite limited functionality. Of course, you can use symmetric keys object for encryption. OpenSSL enc is the utility that implements symmetric encryption from command line. And also we extend the OpenSSL story util that for example, lists keys present by in file system, in your token, you name it. Known implementation. Yeah, of course, the first and main implementation is OpenSSL itself. We have SK management in default provider since 3.5. We have SK management in FIPS and legacy provider for 3.6. For clarity, we implemented two SK managements, one for generic secrets, which can be anything and can be used in theory for any purpose, and the second for IS, which has extra checks that the key is suitable for using with any of IS algorithms. And for test purposes, we have provided implementation of SK in one KDF, password-based KDF1, which is a part of legacy provider, so it should not break any implementation, and also for a CDH key exchange. Try it. Of course, we have, because it's 11 provider, which I mentioned several times already. At the OpenSSL conference, which took place 3 weeks ago, There was a presentation of people from IBM who demonstrated that the approach we used and implemented is suitable for them. They use symmetric keys protected by their processor features. So you see, it works. It's, well, I can't say that it's 100% measure, but it's usable for practical purposes. To be done. Yeah? First, I hope we will be able to land the store support in OpenSSL 4.2. Tomorrow I need to nudge the reviewers again and again. For some future, we will need to provide some so-called encoders, decoders. It's a way how to transform from the, for example, file representation to a key object. And what's more important is simultaneous derivation of multiple keys. Yeah? If you look at the specification of PKZS 11, you see that when you need to get the set of TLS keys, and for TLS protocol you may need either 2 or 4 keys, you have to derive them simultaneously. Currently, OpenSSL uses the approach that it derives a big buffer of necessary length, and then chops it into parts. But when we are speaking about the opaque object, you can't chop anything into parts, right? So it means that we will have to implement, to design first and implement then the API which makes this scenario viable for OpenSSL. And I hope in the distant future we will use only opaque objects or most opaque objects. Again, as Tomasz mentioned at the previous presentation, OpenSSL is open to cooperation, is open to community work, and this week we try to have a meeting of UPSK Special Interest Group where we are going to discuss the next steps and roadmap, and probably someone else, not only Red Hat, will work on implementing it in OpenSSL. We expect support and interest from HSM vendors and users, from PKZS 11 vendors. There was interest from academic community, so let's see how it goes. Thank you very much. Thank you for coming. If you have any questions, feel free to ask. If not, thank you. We are done.
Okay, you already mentioned that, but there is another use case, and that's IBM's mainframe script accelerator. I know you already talked with IBM about that, or do you plan to talk with them? Because we use that for this encryption through various hacks, how to get the opaque key into kernel, and the SKI environment maybe could help there, but definitely someone from IBM have to work on that. So do you talk to them? They are part of this interest group?
Yes, Holger Denger made the presentation, and they already have a preliminary version of the provider that is used. Yeah, I can share the link with you later. Yeah, ping me. If you are interested, then you can check whether it fits your scenarios. You are speaking about disk encryption, right? So yeah. And I hope you will join the special interest group meeting. I think it's on this Tuesday, November the 4th.
Yeah, I will try, but for the mainframes there are actually two parts. First is the disk encryption with crypt setup, and the second is the mainframe tools, and I think they are exactly doing that key downloading, uploading to the HSM. They probably could use OpenSSL for that. I don't know, but definitely that's use case that you have already in RL.
Yeah, I hope they will use OpenSSL, and well, it will allow the using of universal API. Okay, thank you very much. See you.